The null space of an n by n matrix A, written null A, is the set of all solutions of the homogeneous equation AX equals 0. Homogeneous and all equal to 0 go hand in hand. In set notation, null A, the null space of matrix A, is any x in Rn, so that'll match the number of columns in matrix A, where the matrix times x is equal to 0. So that's the definition of null space. Visually, if you take a domain Rn, randomly, well, I don't want to say randomly, mark off a strip in the domain for all your x's, the trivial solution will always be in the null space, because by definition, a matrix A times 0 is going to give you 0, but we're also interested in non-trivial solutions, which could be those types with x values. Anyway, long story short, null space are all the vectors that will map onto 0 in the codomain. Notice that m and n are reversed, so the size of your matrix, the domain will carry the number of columns, and the codomain will carry the number of rows. Null A is the set of all vectors in Rn that are mapped into the 0 vector of Rm. Example, determine if vector u is in the null space of A if matrix A is this 2 by 3. Okay, so for null space, you just multiply. We're going to take matrix A times vector u and see if we get 0. Feel free to put these in your calculator. A 2 by 3 times a 3 by 1, we can multiply, and the answer does, in fact, come out to 0. If you want to hand multiply that or check with a graphing calculator, this vector u is in the null space. Theorem: the null space of an m by n matrix A is a subspace of Rn. Equivalently, the set of all solutions to the system Ax equals 0. You'll have m homogeneous linear equations with n unknowns, and that's a subspace of Rn. Example, let H be the set of all vectors in R4 whose coordinates a, b, c, d satisfy the equations a minus 2b plus 5c equals d and c minus a equals b. Show that H is a subspace of R4. Okay, so what we'll do is we're going to rearrange these two equations. Like, I'm going to subtract d, move it to the left side, and that will create a minus 2b plus 5c minus d equals 0. And in the other equation, I'm going to move a to the front, and it'll still be a negative a because we haven't jumped the equal sign. Then I'm going to move b over. It will go from positive to negative. And then c, I'm just going to scoot down. It remains positive. Long story short, negative a minus b plus c is equal to 0 when you rearrange and reorder the second equation. So by the theorem at the top, H is a subspace of R4 because H is the set of all solutions of the system of homogeneous linear equations. It was possible to write them all equal to 0. This asterisk at the bottom, if your linear equations cannot be written as homogeneous, then the set of solutions won't be a subspace because the 0 vector is not a solution of the non-homogeneous system. Solving the equation Ax equals 0 amounts to producing an explicit description of null space of A. Example, find a spanning set for the null space of A if you have a matrix, and this is a 3 by 5 matrix. It's pretty large. So as far as finding a spanning set, you take your matrix, augment it with a column of zeros, and that'll give it the form Ax equals 0. And then whenever you row reduce, here's matrix A, with the last column being the 0 vector. If you use row-reduced echelon form on your graphing calculator, or on if you found a pretty good website to reduce matrices, and remember I'd emailed you a few suggestions, feel free to use that. If it's out there, grab it, use it. Okay, so that augmented matrix A and 0, if you row reduce it, notice our pivots are x1, x3, and that's it. We do have a consistent system because if you have a row of zeros, they all have to be 0. You wouldn't want something in that last pivot because then it would be inconsistent. Anyway, translating this, x1 minus x2 minus x4 plus 3x5 is equal to 0. And then your second row, x3 plus 2x4 minus 2x5 is equal to 0. And then down here at the bottom, that's 0 equals 0. So that just means that the system's consistent. Excuse me. Our solution vector, x1 through x5, it has 5 entries. If we solve for x1, we move all 3 of these terms across. So think of it as just moving them and changing a sign. Positive 2x2 plus x4 minus 3x5, and that's here in the top row. x2, the second x, there's no pivot, so it's free. x3 is a pivot, and so if you move these two terms over, you get negative 2x sub 4 plus 2x sub 5, and again, that's carrying them over, changing their signs. x4 has no pivot, neither does x5, so x sub 4, x sub 5 are free variables. Okay, so since 2, 4, and 5 are free variables, we're going to make those the weights. Thinking only x2s, we have 2, 1, and then no other ones, all zeros. So 2, 1, all zeros. With respect to x sub 4, we have 1, none, negative 2, 1, and 0. None of them here either. So that would be your column next to x4 as a weight. Finally, x5, we have negative 3, 0, 2, 0, and 1. List those. Again, free variables are the weights. If we take all 3 of these vectors, then we can write the solution vector x as x2 times u, x4 times v, x5 times w, and these 3 vectors make a spanning set for the null space because we put them equal to 0 for the matrix. The column space of an m by n matrix A, written column A or col A, is the set of all linear combinations of the columns of A. So if A is a set of n vectors, then the column space is the span of those vectors. The column space of an m by n matrix A is a subspace of Rm. And by definition, column space of A is any vector B that satisfies this equation for some x in Rn. So basically, we just have to have a consistent system. Example, find matrix A such that W is the column space of A. W is defined as a vector with real numbers A and B in this format. Okay, so what we'll do is, since we have 2 variables A and B, is we're going to rewrite A as a set of linear combinations. The variables will be your weights, 6, 1, negative 7, those are the coefficients of A above, plus B coefficients are negative 1, positive 1, and since the third entry has no B, it's 0. If you take the span of those 2 vectors, which have 3 entries, then W is equal to the span of those two vectors, and so that's how you find a matrix A. As you kind of sort and separate and take the vectors that are the coefficients, put them in order, and you've got the column space of A. Definition: the column space of a matrix A is the set column A of all linear combinations of the columns of A. And so again, that was back to the weights. We have a square matrix A, 3 by 3. Matrix B is 3, 3, negative 4. That's a 3 by 1. Determine whether B is in the column space of A. Okay, so the vector B, what you'll want to do is create an augmented matrix with A and B as your last column. Vector B is a linear combination of the columns of A if and only if this system has a solution. So we set this up, row reduce. We do wind up with a full row of zeros. That's okay, it means it's consistent. So we have an augmented matrix, row reduced, and consistent. Therefore, B is in the column space of A. That augmented matrix tells us that the matrix equation AX equals B is consistent, therefore B is in the column space of A. When a system of linear equations is written in the form AX equals B, the column space of A is the set of all vector B's, or vectors B, for which the system has a solution. So basically create you an augmented matrix, reduce it, and if it's consistent, you're in good shape. Okay, let's look at another example. This is a compare and contrast for null space and column space. Let's let A be a matrix. This one's a 3 by 4, 3 rows, 4 columns. Part A, if the column space of A is a subspace of RK, what is K? Okay, so for column space, you look at your columns of A. Each one has 3 entries. Since each column has 3 entries, column space of that matrix is a subspace of R3. 3 entries in each column, so it's a subspace of R3. Part B, if the null space of A is a subspace of RK, what's K? Now, for null space, remember, we need a matrix X. It'll be a column matrix, but it'll be X1, X2, down to X4. In order to multiply, X would have to be a 4 by 1. Since a vector X must have 4 entries in order for AX to be defined and equal to 0, the null space is a subspace of R4. Okay, so let's try to put this together. Null space is a subspace of R entries of the rows. Each row has 4 entries, so null space will be a subspace of R4. Each column has 3 entries, so that's the subspace for column A. If you can just remember, count the entries in the column, then the null is going to be the rows instead of the columns. Part C, find a non-zero vector in column A and in null A. We're going to look at them one at a time. For column A, just pick any column from A. I randomly chose the second column. Now you will want to make sure you pick a column that's not all zeros. So like if, say this one was all zeros, you wouldn't want to pick it. Alright, so for part C, pick any column from A. Again, I chose the second one. For null space, then you actually have to set up and solve matrix A with a last column of zeros. Row reduced echelon form is what I used on the graphing calculator. So I took matrix A with the last column of zeros to make it homogeneous. Row reduced, I have a pivot in column 1, 2, and 4. So that means 3 is free. Third column doesn't have a pivot, so x3 is free. Now, translating this, you have x sub 1 plus 9x sub 3 equals 0. x2 minus 5x3 is equal to 0. And finally, x sub 4 is equal to 0. So that all those have been translated back to a system of equations. X is the value, column vector for these four variables. Solving for x1, you move 9x sub 3 over, it just becomes negative. To solve for x2, you would move negative 5x sub 3 over, it becomes positive. x3 is free, so I'm making a note here. And then x sub 4 is exactly 0. Now, for null space, the trivial vector where it's all zeros, that works every time. Because if you take matrix A, multiply it by a column of zeros of appropriate number, anyway, enough to make sure the multiplication works, you're always going to get 0. It's the non-trivial solutions that we're after sometimes too. And in fact, that's what we're after here. x3 is free, so I'm going to pick something other than 0, because if x3 is 0, then you just have the trivial solution of a column of zeros, the 0 vector. I'm going to just randomly pick 1, and that's what I did here. Negative 9 times 1. I wrote it as a row because I ran out of paper, and I didn't want to have to switch to another slide. You can write them this way too. But anyway, if x3 is 1, you have negative 9, 5, 1, and 0. That vector is in the null space of A. Sticking with the same matrix A from the last slide, I just recopied it here. I recopied it here for ease. So we have matrix A, two different vectors, U and V, and this is just for extra examples. Part A, determine if U is in the null space of A. Well, we have a 3 by 4 times a 4 by 1, so for null space, you just brute force multiply them. A times U, we're going to compute AU. Please use your calculator. If you're pretty good at mental math, then you can take row 1 times column 1 and do it by hand. Feel free to use your calculator or website, either one. Anyway, long story short, the solution is not a vector or a column of zeros. So no, U is not in the null space of A. A times U did not produce 0. Now we do want to note U has 4 entries. Now we already determined it's not in the null space of A, but it can't be in the column space either, because the columns of A only have 3 entries. So that's a quick way to determine whether that vector is in the column space of A. For null space, multiply them, see if your answer is 0. For column space, if you see where the entries are different, columns in A, columns in U, then they're not in the column space either. Part B, determine if V is in the column space of A. Now it could be because each vector in A, each column has 3 entries, and so does V. So that part's good. Set up A equal to V, because by definition, column space, this has to lead to a consistent system, or it has to be the answer for some vector X. Reduce AV to echelon form. So I took matrix A, which are the first four columns, put in matrix V at the last column, row reduce, and I've got x1, x2, x4. I do want to point out that this is a consistent system. So vector v is in the column space of A. Putting vector v and solving the augmented matrix leads to a consistent system, so v is in the column of A. Also note, v can't be in the null space of A because the rows have 4 entries and v only has 3. So you actually couldn't multiply A times v because v doesn't have a 4th entry. The null space of A is a subspace of R4 because you'd have to have a 4-entry vector to possibly multiply and get 0 for your answer. The word kernel, the term kernel, is the null space of a linear transformation. The kernel of a linear transformation T is the set of all vectors such that the transformation of that vector leads to 0. Kernel and null space are used interchangeably by some people. I did want to mention it because if you have or haven't had abstract algebra, I believe in abstract you see kernel in addition to null space.